Okay, so in this semesters we talk about the size of biomacromolecules, and then the size leading to us to purify the protein, and then protein we absorb on surfaces, and then based on that we culture how to culture the mammalian cells, and also how to image or how to get a chemical information from the such as thin layers of the protein that absorb on surfaces. So we gotta maybe deal with the different topics. In this case here, some soft and biolithography, but maybe we got a little bit different concept before we learning actually go into the depths. The things is why we need and why we have to learn the techniques and chemical biology class in particular. So I will explain these motivations. I give you motivations. I hope they can convince you why we learn that topic. So this is the Ingber, which is the Whitesides and Harvard and MIT professors right now. They're very active currently. And this is a legendary person, George Whitesides. He's got a lot of achievement in chemistry and biochemistry, also physical chemistries and many other different areas that can open a new different directions for many subsequent scientists to open their eyes. So one of this, especially also the Miller Research is now also University of Chicago professors now going to the Northwestern University. So we talk about, the geometric control of cell life and death. So cell is surviving or cell is going to be die depending on their geometric control. So let's get into the, before we get into the detail, actually you can see one of the image they got obtained, and this is the following. So this is their design of the surfaces. Okay. So they want to have the mammalian cells, the cell from us, the skin cells or brain cells, no matter what the cells is, they want to stick in here. They want to stick in here and stick in here and stick in here, also in the area they control. So the title is controlling the geometry of the cell. So see, they're matching. Actually, the cells actually they adhere on surfaces, and then see how the fate they're gonna leave or they're gonna die, depending on their environment. So that means that we live in a very small spaces, or they live in very large space. Or even the large spaces looks like to be happy, but probably not happy. In some cases are not happy. So they got a very fundamental questions themselves how they behave for this. But today's topic is how they control the cells behavior, not attaching to this the other area, only attaching to only this designated area that they can control. But how they do it? I mean, in the previous cases, when I teach you about the culture of the mammalian cell, is the, what is it? And the rule number one is they mean that mammalian cells. Mammalian cells don't attach surfaces regularly, but they only attach the cells when the surfaces that have protein on it, right? So it looks like the proteins 1 nanometer, 2 nanometers layers of protein on a transparent glass or silicon wafers or titanium. You cannot actually see it. That's why I teach you XPS, AFM, that how they image, how they chemical image and physical image you can information you can get. So you cannot actually control. It's very difficult to control the behavior or control the protein levels. But you have to have the way to control the protein absorptions on the surfaces, because as mammalian cells only goes to the area that proteins are absorbed on. So that means, in other words, it's very easy that somehow these investigators and the author of these papers, know how to point their proteins, since the proteins that cells can recognize, can control this, absorb on this only area, not this area, and this area, but not this area, not this area. So they can actually basically control this ability to do it. So see here also, same, see that, you see this, the attachment, 25 micron, 10 micron, or no beads that can control the cells here. Same protocol, same method they can control. So this is how they do it, and then see the result out of it. And maybe this is not important, but this kind of technique that the next time we talk about a little bit more about it. But based on these techniques that see the apoptosis percentage and the DNA synthesis percentage. So what is that? These are opposite levels of the indicators. So see, the DNA synthesis means that cells are dividing or cells are alive, because to maintain these cells' ability, divisions has to be an active process. Then DNA has to be synthesized to divide the cells. The apoptosis is the cell death, but this is not a necrosis. The apoptosis necrosis difference is the necrosis is just the physical damage, and the cells are punctured away and they die. But apoptosis is cells based in the integrity, physical integrity is in there, but the apoptosis is programmed death. So I have to be died in 10 days after. I have to be died in 5 days after. So the apoptosis means a program. You have to be died in a certain period of time. I will give you maybe 2 weeks. I will give you 1 week. I will give you 1 day. Then you have to die in that way. So this is apoptosis. So see the apoptosis, but this is adhesive island area, which is you can control the island area. The cells are how many they leave, how much area they can obtain, how they grow this in this area. So this now the adhesive island smaller, or adhesive island in this, I guess is a critical point of this. Maybe this is the 500. Probably this is the 300 micrometer square. In this area, be lower than this, and then it's too small to leave for the individual cells to maintain this basic metabolism. But after this, it doesn't matter. I mean, we have this area and that area, doesn't matter. Actually, they can survive. So without this technique, and we don't know that how many provided the spaces we can, how much spaces we can provide for each cells to control the mechanisms of metabolisms of the individual cells. See, this is one of the technique in here, and also maybe I can provide a different example, which is, I guess, more interesting examples in here. This is basically image of the scanning electron micrograph SEM image. The difference between the previous study and now study is there is no geometrical. Basically, the previous one is flat. Right? This is flat. This protein is island here, island A is here, and B is here, and C is here, and then the cells recognize the island and they leave in there. But this study is a little bit different. The study is they have a pillar formations, and then the protein the cells then recognize exists on top of it, not in the bottom. So the cells I can see in the A panels and B panels. So A is you can have pillars in here, and then they see it from the side. Now the B is from the top. So there is a difference, but it's the same, basically same devices. But see, the cells are attaching an individual pillar, which is a pillar, I guess, the 2 micrometers diameter and the 3 micrometer distance center to center. So this is from here to here, the 3 micron. And the individual micron, the diameter is a 2 micron. So this is kind of very small. Right. So this, now here, this 8 micron, cells are about 8, 16, and 20. About 20 microns that is corresponding to, is right about corresponding to our previous classes, so it makes sense. So they're attaching, see, the edge of the pillar over here, so they actually bind and then they attract. It means that cells not only residing safely on the surface, also they're very active. They provide actually force to have some certain levels of metabolisms for their life. It means that if you think about the neuron, so neuron has a cell body and then there is another dendrite goes in the more far away for the communication between cell to cell. And that's why if you touch a neuron, we're feeling this the sensing because of the neuron cells are acting very, very actively and fast in our body. So if you think about the neuron cells and they attach, they connect to each other. So if you think about this, more interesting because if your cells, especially neuron cells, are living on top of the pillar, that you have maybe different situations of providing this informations, but the receiving information might be probably different, or probably similar to actually what is happening in our body. So nobody knows actually. But the people, now we scientists getting knowing more and more about the neuron cells or the regular cells in our body that they actually feel how they're comfortable in our environment of the cells, their environment, because the protein provided the rigidity of this is kind of tight, right? This is the rigidity of our tissue. This is a kind of brain is kind of more soft. Bone is very, very stiff and hard. So the actual cells and sensing, this is a kind of hint that indicating that cells can actually see the certain existing certain force they can provide it. And you cannot observe this when it's under the bone, right? So this bone is a different behavior. So cells are adjusting to that environment. So that bone cells probably have a different signals because of the rigid. They are living at rigid surfaces. The regular cells are soft surfaces like our skin, and they provide different signals. But as scientists, how we know it? Then we have to have certain techniques, right? Certain techniques to have such as pillars or squares, spheres, or flat surfaces. But the protein has to be localized in our controlled way so that the cell only recognizing that area on which the proteins are existing. So that they can bind to it, and then they have started behaving very, very uniquely on top of the surfaces, in which it's too detailed to explain all of them because it's of the undergraduate classes here. But in this study, actually they measure the force. Actually, see here, delta x, Young's modulus, and deflections of the post. Post is individual pillar. So you got equations, and you see this. The delta x means the pillar is actually moving in certain directions until it reaches delta. The original delta x is 0. Delta x1, this is delta x, and that is provided delta x informations. Length, radius, the E is Young's modulus, which is intrinsic properties of the pillar, how they soft, how they rigid, and then you can calculate the force. So that the means, if you know this, the distance between the pillar movement, then the cells we can figure out how the force. Cells can actually attract this, pulling this pillar toward their body, which is very interesting because we probably before these classes we don't know the cells actually can can provide a force out of the external area, then the attractive we cannot imagine. But actually cells are very dynamic, then cells to cell or cell to environment, they can pull and give the force out of it, and then they have an active communication in a not only chemical way, but also the physical way for their communications. So next time, how we control this, how we can make it basically, how we can control the positions of the protein by terms of the soft lithography. So we can learn a little bit more of it. So this is the first part of this whole process. Thank you very much.